Hey, I'm Dave. Welcome to my shop. Today, I'm going to take a Raspberry Pi and drag race it against all comers. Now, even I'm naturally intuitive enough to know that a Pi5 is faster than a Pi4, which is faster than a Pi3, and so on. But I don't have a good sense of where they rank relative to one another, and perhaps more important, how they rank relative to a mini PC or even a full desktop CPU. How much faster is a full Threadripper than a Raspberry Pi 5? Is it 10 times, 100 times, or 1,000 times faster? We'll find out today as we rank these single board computers relative to each other and relative to modern desktop CPUs. I've gone into that bin that we all have. No, not the big bin of cables in the closet that your wife complains about, but the little Tupperware container of Raspberry Pis and stuff. And I've put together a long list of contenders to go head-to-head with the classic Pi. We're going to bust out the GitHub Primes project and crunch some numbers to see just how each of these little PCs ranks against one another. From the Beaglebone Black to the Pi3, the Pi4, the Pi5, the Jetson Nano, and more. And then we'll roll out the desktop hardware and test it on a 16-thread Zeon Silver and even a 96-core overclocked Threadripper to give you some context of where they all rank relative to each other. I think you'll be shocked with the results. I know I was. To get started, we need a benchmark that we can run across a wide range of hardware and that will really focus intensely on the CPU and memory access. There are more comprehensive benchmarks available, like Geekbench, but in this case, I don't really care how fast the Pi can recognize vectors in a dot cloud to solve AI tasks or whatever else it does. This isn't a decathlon, this is a drag race, so we're going to go right to the Primes to settle the score. And if it's Primes code you're looking for, Google GitHub Primes and it will take you to the Dave's Garage Primes project on GitHub. In this solution, you'll find the same PrimeCiv algorithm expressed in almost 100 different computer languages, from Ada to Zig and everything in between. Each night, the project runs the benchmarks for every language and posts the results on a leaderboard, and I'll put a link to those results in the video description so you can compare the languages and see which is fastest. We're going to use one of my own solutions, which is the C++ project known as Solution 2. It has a little batch file that will compile and run the project almost anywhere as long as you can get the CLang compiler installed. We'll enlist in the project from each of the test machines and then build and run the PrimeCiv. When we run it, it's going to solve the primes up to 10 million as many times as it can in 5 seconds. Now, every good benchmark needs a baseline to compare against, and for us it's going to be the Beaglebone Black. The Beaglebone is more of a European phenomenon and they're less common in the US, but you can still get them cheap overnight from Amazon and they run a full Linux installation, so they're perfect for our purposes. The Beaglebone Black features a 1 GHz ARM Cortex-A8 CPU and 512 MB of DDR3 memory. I've installed NeoFetch on each system so we can see a system report before we kick off the benchmark on that particular machine, and it will confirm the hardware stats for us. To get the machine ready for testing, I'll install the CLang compiler as my first step. That will take a few minutes, which I'll fast forward through here until the prompt returns and I can enlist in the source code. Even though I'll only be using the single C++ solution, I'll still grab the entire project because it only takes moments to do so. One change I did have to make was to take out the architecture and tuning flags from the CLang command line in order to get it to compile on the Pi. It takes about 30 seconds to compile the code on the Beaglebone, which doesn't bode very well for performance. But soon enough, the Primes test kicks off and runs for 5 seconds. As soon as it produces this result, we can see that the Civ was able to complete 8 passes. The average duration for each pass was 0.69 seconds. And honestly, the fact that any of these tiny boards can solve the primes up to 10 million in under a second impresses me. The first PrimeCiv I ever wrote was in BASIC on a Super Pet, and even heavily optimized, it took 6 seconds to solve the primes up to just 1,000. Still, in the output we can see that the Civ only ran on one thread, which is because the Beaglebone only has a single core. It should be a fairly significant step up to the Raspberry Pi 3 then, as the Pi 3 features 4 independent cores, each running at 1.2 GHz in stock form. Compiling there takes about 15 seconds, or about half what it did on the Beaglebone. There's only a single source file, so it can't do a multi-threaded compile, but if it were a larger project, I would guess it would compile about 6 to 8 times faster than the Beaglebone in a sustained parallel compilation test. When our results come back, we can see that the Pi 3 was able to complete 22 passes using 4 threads, with each pass taking about 1/4 of a second. Overall, that's about 3 times faster than the single-core Beaglebone. But with 4 times as many cores, why isn't it 4 times as fast? Well, my suspicion is the memory bus. Since a PrimeCiv spends most of its time on each of the CPU cores computing bit masks and walking through large swaths of memory, having 4 threads all competing for the same memory bandwidth means that the gains from multi-threading aren't going to be quite linear unless there's a lot of memory bandwidth to take advantage of. Next up is the Pi4, which has been pretty much the gold standard for the last couple of years. The Pi4 still has 4 cores, but they bump up to 1.8 GHz, which should yield a significant performance bump. We'll run the script that kicks off the benchmark and wait our 5 seconds before the results come in. When they do, the final score for the Pi4 is 41 passes. That's almost double the performance of the Pi3 and 5 times the performance of the Beaglebone, so now we have a good sense of how the Pi4 performs relative to the Pi3. But of course the Pi4 is already several years old and the Pi5 is generally available. I grabbed one, marked up as it was, just for this test, so let's put it through its paces. As we did with all the other Pis, I've enlisted in the source, and then we'll run the benchmark script on the Pi5 to generate the results. And with each pass taking less than 7/100ths of a second, it's able to crank out a final score of 73 passes in those 5 seconds. Compared to the 41 of the Pi4, that's not quite double. I'm confident that the raw computing power of the CPU cores is still likely double that of the older Pi, but that we're still somewhat gated by my memory contention, so again our score doesn't quite reflect that delta. Big picture then, the Pi4 is about twice as fast as the Pi3, and the Pi5 is again about twice as fast as the Pi4. But what if you needed something even a little faster? Well, somewhere in my bucket of tricks, I've got an Nvidia Jetson Nano, a single board computer intended for AI applications. I'm not sure how it stacks up in terms of raw compute versus the Pi, but the heatsink is massive in comparison, so perhaps that's a good sign. The Nano has a quad-core ARM Cortex-A57 processor at 1.5 GHz. My version only features 2 GB of RAM, but that'll be plenty for the Prime Civ. We'll bring up the console, this time on the Jetson Nano, install the code, install CLang, and run the benchmark. When the compile kicks off, we can see that it takes about 4 seconds. That's a far cry from the 30 seconds that we started with on the Beaglebone. And as soon as the compile finishes, the benchmark kicks off for its 5-second run. When the results come back, we can see the Nano achieved a score of 189 passes. That's more than double the score of the Pi5, and the Nano is already several years old, and these days you could even step up to the Jetson Iron Nano, which is rocking 6 cores and even higher performance. Suffice it to say that the Nano performs quite a bit better than the Pis. One nagging question I've had for a long time is how well these boards actually stack up against desktop PCs. They seem pretty fast, but how fast are they by comparison? I decided to throw 3 of my systems into the mix. First, there's the Storinator, which is running a Zeon Silver 4216 CPU with 16 cores and 32 threads. It runs at a base clock of 2.1 GHz and a maximum boost clock of 3.2 GHz. It's a middling processor by today's standards on the desktop, so let's see how it runs. The compilation took less than a second, and while there were a few warnings about the vectorizer not being able to optimize a few of the loops, they're not in critical performance paths, so I just left it to run the Civ for 5 seconds and await the results. And so how does a fairly banal Zeon Silver processor stack up? Well, it achieved a score of 5,536. And going from a top-tier single-board computer to a middle-of-the-road server chip, we jumped from 189 to 5,536. That means the Zeon is about 30 times faster than even the Nano was. Stepping up the performance ladder a little further, we move on to test the Civ on my M2 Mac Pro. Equipped with 12 modern ARM cores, the only thing that might hold the Mac back a bit is that the ARM instruction set doesn't have a way to directly set a bit into memory, which is an operation that the Civ performs a great deal. Instead, you have to load the value into a register, operate on it, and save it back to memory. Of course, the CLang compiler takes care of all of that for us, and as soon as the benchmark runs, we see it turn in an impressive score of 9,471. Even though the core count is lower than it was on the Xeon, the M2 Mac Pro's clock speed and core architecture allow it to pull ahead of the Xeon by a wide margin. But if we're going to be silly and compare single-board computers to modern desktop processors, we might as well go all the way. As far as I know, my AMD Threadripper 5995WX is currently the performance champion. Sporting 96 cores and 192 threads and 512 gigabytes of memory, there's no question that the Threadripper will top the leaderboard, but by how much? Well, once the 5-second run is complete, our answer is revealed. The Threadripper scored an amazing 128,154, which is about 1,600 times faster than the Raspberry Pi 5. And so if your question is, how much faster is a modern high-core desktop chip than the fastest Raspberry Pi, the answer is about 1,600 times faster. Let's put the single-board computers on a graph without the desktops at first so that we can see where they rank visually. We start with the Beaglebone Black, and from there we can see the increase in performance as we move to the Pi3, the Pi4, the Pi5, and the Jetson Nano. As soon as we put the desktop chips on the chart, however, it's going to mess up the scale entirely. Here's the same chart but with the Xeon M2 and the Threadripper depicted. Hopefully, this visual gives you perspective on just how powerful our modern desktop processors are. Now, if you found today's episode to be any combination of informative or entertaining, remember that I'm mostly in this for the subs and likes, so I'd be honored if you consider subscribing to my channel and leaving a like on the video. And if you're already subscribed, thank you. Please do check out the free sample of my new book on Amazon, The Non-Visible Part of the Autism Spectrum. It's intended for folks that don't have an ASD diagnosis, but who suspect they might have a few characteristics that put them somewhere on the autism spectrum. It's everything I know now about living a successful life on the spectrum that I wish I'd known long ago. Check it out at the link in the video description. In the meantime and in between time, I hope to see you next time, right here in Dave's Garage.
And that's all I have to say about that.